All right, let's get started with Chapter 9, the derivative. In the first section, 9.1, we're going to look at the concept of limits. So you can see the definition in front of you. You can go ahead and read that. And then also look at the note here on the bottom. This is important. The existence or non-existence of a given function at x equaling a has no bearing on the existence of the limit of the function as x approaches a. So I'm going to explain this definition, first of all, by looking at the concept graphically. Okay, let's go ahead and use a graph to find the limit if the limit exists. So what we're going to do is we're going to use the graph of the given function f to determine the limit of the function f of x as x approaches a at the indicated value of a, if it exists. All right, so what does that mean then? Well, here's all you have to do graphically to find a limit, if the limit does exist. What you're going to do is, first of all, look at what you're homing in on, which is a equaling -1. So there's -1. There's a equaling -1. All right, right there. There's our x-axis. And this is a equaling -1 right here. So the graph is in red of the given function f. And all you have to do is see if when you get closer and closer and closer to -1 from both the left side and the right side, are you getting closer and closer and closer to some specific y value? So again, as you approach from the left and the right, are you approaching the same y value? Yes, you are. So for letter A, the limit of the function f with x in its domain as x approaches specifically -1 will be equal to 2. Note, just like I shared with you initially, that the existence or non-existence of this function at x equaling -1 has no bearing on the existence of the limit. All right, the function is actually not defined here. It is, however, defined here. So we also should understand that f of -1, f of this x value, is equal to 1. But this isn't the limit. The limit is what y value, if any, what y value, if any, are you getting closer and closer and closer to as you approach the x value from the left side or the negative side and the right side or the positive side. So in this case, it would be 2. All right, so letter B. Letter B, again, we're looking at a similar situation here. We know the function does exist at x equaling 3. So f of 3 would be -3. F of 3 would be -3. But we do not care about that when we're talking about a limit. So the limit of this given function f with x in its domain as x approaches this a value, 3, would be equal to what? Again, you're looking at this thing coming from the left and the right. Are you getting closer and closer and closer to a specific y value in space? Yes, you are. It's not equal to this y value, but that doesn't matter. That's what a limit's all about. What are you getting closer and closer and closer to? You're getting closer to -2. That'd be the answer for the limit of the given function here, f as x approaches 3. Let's do one more graphically. So in this case, we are actually looking at trying to determine the limit of a given function f with x in its domain as x approaches -4. We're going to see if this exists or not. Well, the function is clearly defined in this shaded region right here, this shaded in circle. So the value of the function at -4 would be 2. But again, that does not have any bearing on the limit. What has to be true if the limit exists is when you come from the left and you come from the right, Are you hitting the same exact y value? Are you homing in on the same y value? No, we're not. In this case, as you approach the -4, the x equaling -4 value from the left, you're getting a 2. As you approach the same x value, -4 from the right, you're getting a 3. Does 2 equal 3? Are those the same? No. Therefore, the limit does not exist. D&E does not exist. Let's look at another example. Find the limit of f of x as x approaches 5, where f is defined as the following. This is a piecewise function. So what does this mean? Well, let's look at this actually, even though we don't have a graph in front of us, let's go ahead and look at this graphically. So let's create our own graph based on this information. Okay, so let's see. We have 5. If x does not equal 5, okay, so let's put a 5 about right there. All right, there's our 5. This is, of course, our x-axis. This is our y-axis. So what this says is the function f is going to be equal to 1 everywhere x does not equal 5. And remember, f of x is the exact same thing as y. So y equals f of x, right? So I'm going to put a 1 right here. And again, let's look at this again. F of x is equal to 1 everywhere x is not equal to 5. So what I'm going to do then is locate 5 on my x-axis. I'm going to put an unshaded open circle there. And I'm going to draw in a horizontal line. So this represents the fact that the graph is going to be equal to 1, y is going to be equal to 1 everywhere except for when x is equal to 5, right? And the second part of this piecewise function says that, well, the graph of f is equal to -2 if x is indeed equal to 5. So that would be a shaded in point right here. So that's what this piecewise function would look like graphically. Now I think it's easy to determine the limit of this. Again, we know the function exists at 5. It's equal to -2 at that value. But we don't care in terms of the limit. All we care about is what the curve or line is getting closer and closer to as we approach that x value from both the left and the right. And you can see that, well, it's a constant function at that point. So it's homing in on what y value? 1. So we would say the limit of this function f of x as x approaches 5 would be equal to 1.